Okay, so I wanted to make this video to show you guys a few different graphing techniques for our trig functions. I'm going to assume that you have watched the other video on the basic way to graph basic trig functions like sine, cosine, tan, secant, cosecant, and all of that. But what we want to rely on is something you should know from 171, which is graphing transformations. So we're going to start by looking at that. F of x equals 2x squared and f of x equals x squared. All of you know the graph of x squared, just a nice parabola. And we don't necessarily need to take the time to go into great detail here, but if I do 2 times x squared, if you remember your transformations, essentially that gets bigger faster. And it'll look like this. Here at 1 we get 1, here at 1 we get 2, so this one is inside of that, or it gets steeper, faster, however you want to say it. The actual mathematical way to write it is called a vertical stretch or compression. It's a stretch if the number you multiply by is greater than 1. It's a compression if the number you multiply by is between 0 and 1. And again, you should recognize that from 171. But the good thing is, if you recognize that, then the same rules apply for trig functions. Here, if we take f of x equals sine x, we know the basic graph. I'll just do one period of the wave. Well, if I take f of x equals 2 sine x, that's just multiplying this function by 2, which is the same as multiplying this function by 2. It's a vertical stretch. As far as how it looks, well, at 0, I'm still going to get 0, because 2 times 0 is 0. At pi over 2, I normally got 1, now I get 2. At pi, I got 0 before, 2 times 0 is 0. At 3 pi over 2, negative 1 times 2 is negative 2. And then at 2 pi, I get 0 again. And we can see the wave looks the exact same. It's just stretched vertically. So if you remember your transformations here, they'll apply here the exact same way. In terms of how we describe this in trig, we actually say that this number right out in front is the amplitude. The regular sine wave has an amplitude of 1, because right out in front here, there's a 1. We don't write it because it doesn't matter. Now that's 2, so the amplitude becomes 2. The wave goes from 0 to 2 and 0 to negative 2. Good. One thing I also would point out, as I pointed out to my seated class, we have 6 different trig functions, and we have about 6 different transformations. I'm not going to do a graph of every single transformation, every single combination of transformations on every single trig graph. We'll, for the most part, rely on using sine and cosine, and then it'll be up to you guys to kind of expand on that by way of homework and Alex and stuff like that, to mess around with these transformations on your own with other trig functions. So, let's see. Well, if we go back over here, what else did we do? If before, when we did transformations in 171, we could have x squared, and then we could have x squared minus 2. What's the difference between those? Well, if you remember, that's a regular parabola. This is the regular parabola, and then you shift it down 2. In 171, I think we called it a vertical translation. If that's negative, you go down. If it's positive, you go up, and you're good to go. But logically, the exact same thing should apply for our trig. So suppose we have f of x equals sine x, and f of x equals sine x plus 4. Well, if we go to graph it, let's see. That's the regular sine wave, so we could sketch that really fast. And here we'll even mark to make sure we're clear. That's positive 1, down here is negative 1. Now we want sine x plus 4. Well, just using what we know from 171 in our transformations, that plus 4 will just shift my graph up 4. So, I was at 0, 0. If I go up 4, this is going to be hard to draw to scale here, but we'll say this is 0, 4. And then here, it was at 1. If it goes up 4, now it's at 5. Then it goes back to 0, my equilibrium, which is at 4. Then it goes down to its minimum. Its minimum was -1, but we went up 4. So -1 plus 4 is +3, which we'll say is right here. And then we go back to our equilibrium point, our 0, which in this case is shifted up 4. And if we sketch it, well, there we go. There's the exact same sine wave. I know this one's a little flatter because this whiteboard is limited. But essentially, we took this graph and shifted the entire thing up 4. And that's it. So the one thing I would stress as we go through these transformations is a few more we want to do. They're no different than they were in 171. As long as you have a basic function to start with, whether it's a quadratic, a cubic, an absolute value, a sine, or a cosine, draw your basic graph, and then alter it using the transformations you know. So, just for fun, we are going to combine those two transformations. So, suppose we have f of x equals 4 sine of x plus 2. As you're doing these, I would encourage you, and on some of your homework I may actually make you, list out all the transformations. I have a 4 out in front. What is that? That's a vertical stretch, or in terms of trig, that's my amplitude, 4. I have a plus 2 on the outside. Well, what does that do? That's a vertical translation. And it goes up 2. Now sketch my graph, and hopefully we will have room on this board right here. So let's see, rather than drawing the regular sine graph, we'll just draw this one. Let's see, start off with, as we start building these graphs, start by listing your 5 basic x values, the kind of standard, I think your book calls them key points or key values. The 5 basic ones, let's see, you need a starting point. These are not the y values, these are just the x values we'll use as a guide. There's 0. My period is 2 pi, so we'll call this 2 pi. Then the midway point between them is pi. And then the midway points we've been using, pi over 2 and 3 pi over 2. As long as we have those 5 points, we can plot the points and be good to go. Those will change as we do some more transformations on our graph, but for right now that works. So now let's see. The sine wave starts at its equilibrium. Normally that's 0, but I'm shifting up 2, so the equilibrium is now at 2. Then it goes up to its maximum. The maximum is normally 1, but I changed my amplitude to 4, and then I'm going to go up 2, so now the maximum should be at 6, which we'll say is right here. 2, 4, 6, that'll work. Then the sine wave goes back to its equilibrium, which in this case is 2. Then the sine wave goes to its minimum. The minimum would be -4 with an amplitude of 4, but then we shift up 2. -4 plus 2 is -2. So we'll say -2 is right about here. And then at 2 pi, I go back to equilibrium, which for me is 2, right here. And now, assuming I did that right, if I connect the dots, well, there we go. That's a nice sine wave. One of the other things I would stress as far as doing this, to make sure when you're doing it for written homework and I'm grading it, list these x values out. Again, for right now, they're the 5 basic ones we've been using. As we do more transformations, they will change. But whatever they turn out to be, list the 5 x values. And then as we start making our graphs bigger and smaller and shifting them up and down, list the y values that are important. We have 6 our max, 2 our equilibrium, and down here we have -2 our minimum. Then I can actually see that you did all the transformations correctly. I'm going to stop this video right here because we're going to jump to a few more transformations and they might take longer than this video would let me do. So I'm going to have several videos on all the different transformations for you guys to look at.